Hello and welcome to the Fall 2020 ET350 Final Motor Competition. This is a virtual project fair that we are holding, and what we're going to do is have 26 students present their final brush DC motor designs. What we'll cover in this presentation is the contest and scoring, and talk about the provided parts and equipment, and then all 26 students will share their approximately 2-minute presentation with 5 slides. And the last part, we'll go over the results of who won. The competition was set up as such. We had each student build a brush DC motor that you can see in the middle. They 3D printed a bat here, and their task was to hit a little squash ball as far as possible. Now they could only set the ball at a maximum height of 42 inches. They had to maintain a 5-inch by 5-inch max height and max diameter volume constraint. They were provided a power supply here that could provide 24 volts and 15 amps. And then they had to operate at a safe distance away, about 2 feet, with a remote trigger here. The way we scored them, and this was for extra credit, not their grade, but the way we scored the competition was the student that hit the ball the farthest would get the max 100% score for distance, and the student that hit the ball the least distance would get the 0% score. Now for weight, we actually did factor that in, and that factor would come in where the student with the lightest motor would actually get the highest score, and the student with the heaviest motor would get the least score. And because we did want to encourage distance, we actually weighted the distance at twice the weight of the mass score. That's why there's this 0.5 right here. But we added this up, this weighted score, and that's how we computed the final result. We provided every student with a 3D printer, and so that way we didn't let COVID-19 stop our projects. The students were able to 3D print all their designs in their dorm. We provided them with a roll of filament, magnets, magnet wire bearings, 6mm shaft, a commutator, which you can see down here, a pair of brushes, of course the power supply, a power cord, some epoxy to glue everything, and all thread to connect everything together, and some hardware along with shaft collars, and of course the squash ball so that they could have something to hit. And you can see all the kits that we had assembled and distributed to the students through our wonderful makerspace. And this is the competition bat that they all used. I really hope you enjoy the rest of these presentations, and thank you.
Hello, this is an exploded view of the motor. As you can see, the large piece is the stator with the rotor inside, with 2 end caps on the left and right of it, with this support right here. A better photo of the rotor and the stator is to the left. Now this has 6 poles of alternating field, magnetic fields, as well as 3 coils wrapped in parallel. This is electromagnetic diagrams. To the left is the power angle, where there's full current going through the coils, in which they interact with the magnetic field, causing a Lorentz force, causing the rotor to spin in a clockwise direction. To the right is the dead zone angle, in which there is no current, because the insulation on the commutator here covers the brushes, so there's no current at all, and therefore there's no Lorentz forces. Here are the project photos. To the left is the soldering operation, in which I was in the makerspace, and it was really nice working there. Here in the middle is myself in the 3D printer with my newly printed rotor. And then to the right is a video of the changing magnetic field of the stator, in which you can see the magnetic field changes with the little polarity detector. Now right here is the video of my motor running and hitting the ball. Now unfortunately it didn't go as far as I wanted it to, but it still hit the ball pretty good. Totaling a little less than 2 pounds and 6 feet. Here's for acknowledgements. I really appreciate the makerspace from Aaron Cole's help to availability of the tools. It really helped a lot. And Professor Chang-Siu for teaching this course and general help with my designs. And then Patrick, Ben, and James for help with just general assembly, as well as just quick tips I can always message them out. And then Anthony Gonzalez for the moral support. Thank you.
2 brushes. Well, continue. Thank you.
Forgot to hit record. Sorry, guys. Please accept the recording.
How do I go to the next slide?
Oh, yeah. Just let me know.
This here is my electromagnetic diagrams. Basically, the current comes through the brushes and around each wrap, out back through the brushes. And then these are my magnets, north and south. And those cause the force that spins the motor. If you look at the bottom, you can see that even when 2 commutator sections are touching on each side, the motor still works. So yeah, next slide. Here's some pictures of the actual motor after I made it. This is the assembly on the left, and this is the commutator sections that I was talking about before. Here's my video. Went about 5 feet on that hit. My motor was about 2.5 pounds, and like I said, it went 5 feet. My acknowledgements, I want to thank Mr. Chang-Siu, Mr. Clyde, and also Aaron Cole for helping me in the makerspace.
Yay. Thank you, Marquez. Okay, so let's go with the next one. All right, Mr. Joe Barty, you are up, sir. So let me get that slide going. Come on, PowerPoint. Give me 1 second. PowerPoint, there we go. There we go. Okay, we're good. All right, Joe.
So this is my motor design. I designed 2 end caps, a stator, and a rotor. And this image shows how the stator fits into the, or how the rotor fits into the stator. Next slide. And my diagrams, they show how the commutator sections are set up. So the positive and negative brushes send current through the coils of wire. So the positive brush sends current around the coils, and the magnetic forces cause a force onto the coils. And then the next diagram shows the dead zone, where no forces are acting on it because the coils of wire are directly in between each magnets. Next slide. I think the biggest challenge was getting the commutator section correctly. I had to retry a few times to solder and align the commutator so the brushes were sending current through the coils at the right moments. Next slide. Here's my video. My dog.
Nice.
And that went about 10 feet.
Nice.
So the weight of my motor was 2.6 pounds. And I would like to thank Dr. Chang-Siu and Professor Clyde for helping me out so much.
All right, good job, Joe. Thank you. Sorry that you only get my clap. That's the downfall of Zoom, but it is what it is. All right, Mr. Ben Bashore. Let me get your slide going. Okay, give PowerPoint a second to warm up. Come on. There we go. Okay.
Hello everyone, I'm Ben Basher. This is my motor project for ET350. So the diagram on the left-hand side, we see the motor totally assembled. And then on the right-hand side is a more exploded view, how all the parts fit together. Go to that next slide, yeah. Here are the electromagnetic diagrams. On the left, current flows in such a way that the current flows through the coils in such a way that the Lorentz force causes a counterclockwise torque at all 6 coil locations. And then on the right-hand side is the motor in a dead zone. No current is flowing through the coils, therefore no force is developed. We go to the next slide. So a small thing that I'm rather proud of is designing a housing for these brushes. So those little brass pieces, they need to be held in a very exact location. So I sat down with a pair of calipers, and within a few iterations, I found a good rounded rectangle shape. I incorporated that shape into my final design for my end cap, as well as a handful of other people also used the same dimensions in their designs. And another thing was sitting down to wind the rotor. I went through a total of about 800 feet of 24 gauge wire. So just sitting there for a few hours, winding. We go to the next slide. Just a quick demonstration of the project working. And finally, results and acknowledgements. So there we have the weight and the best distance. I'd like to give a thank you to Professor Chang-Siu, Aaron Cole of the Makerspace, and Chris Mulhauser for handling a lot of the backhand logistics and ordering.
All
Thank
right. Thank you, Ben. Very nice. Nicely done. Okay. The next we have is Nate Bayer. All right. Okay, let's go PowerPoint. Yeah, perfect.
Everyone, here's my exploded view of my motor. To the left, you can see a topographical view of the motor with all the labels. And here on the right, I have the exploded view. Next slide. So looking at the left diagram at the 0 degree reference position, you can see the brushes have voltage applied across them, indicated by the positive and negative leads. Sections that are in the contact with the brush provide a path for current to flow and complete the circuit. As current flows through the windings, a force is created due to the presence of a perpendicular magnetic field represented by the letter B, which flows from the north pole of one magnet to the south pole of another. This force produces a torque in the counterclockwise direction. Looking at the right diagram, the motor has moved 30 degrees and is now solely in contact with the green commutator section, which provides a path through just one winding. So here's a couple photos. I have my assembly to the right or left. I have my armature windings and the brush commutator and end cap on the top right, and then my stator with the magnet on the bottom right. Next one. So here's a video of mine getting the ball.
Right.
Kind of hard to see, but I think the total distance is around 5 feet, so 60 inches. The max height was 37.5 inches, and the total weight was roughly 2.2 inches, or 2.2 pounds. Couldn't have done it without the help from Professor Chang-Siu, Professor Clyde, the ET department, Aaron Cole at the Makerspace, and all the random people on YouTube who help with the CAD tutorials.
Nice, nice. All right, yay, Nate. Great job, thank you. Okay, let's go to the next one. Okay, next we have up is Kelly Bodeman. Okay. All right.
Hi everyone, I'm Kelly Bodeman and this is my overall design. I decided to go with a vertical motor. So I used 6 alternating magnets, 2 brushes, and 3 armature loops. If you look at the picture on the right hand side, you can see I made like a little divot for my brushes and I added like little studs to make sure it like locks the end cap to my stator. And then I also added like little ribs just for like a design aspect and to make it lighter. Next slide, please. And then this is my electromagnetic diagram. You can see on the left-hand side that is displaying the Lorentz force. You can see the magnetic field goes from north to south. The current is going in on the top, which means using your right-hand rule, this motor would be spinning clockwise. And now if we look at the picture on the right-hand side, we could see how my commutator was wired up with the brushes. So I shorted 3 for the positive and 3 for the negative. I used 3 or 6 parts of the commutator. All the rest were like dead zones in between. Next slide, please. And so here are some pictures during my building process. You can see my stator 3D printing, and then my rotor, and then winding my rotor, and then after I soldered all the shorts together. And then when it was all done, you can see that it's standing vertically. And next slide. And then the results were 7.1 feet, and then 2 pounds. The meters is wrong. It's 1.7 meters or 1.338 kilograms. And then so much thanks to Professor Chang-Siu and Professor Clyde, and especially the ET department for like letting us be able to do this motor project. It definitely wouldn't have been the same. Thank you.
All right, Kelly, great job. Thank you. Good job. Okay. All right, next. Okay, so the next we have is Mr. Aidan Cabelera. All right, Aidan. Okay, give it 1 second. PowerPoint's thinking. It's like, do I want to go? Come on, let's do it, PowerPoint. There we go.
All right. Hello, everyone. My name is Aidan Cabelera, and this is my motor. You can see my results on the first slide. I got a pretty measly 4'7", but my motor was also very light. I actually went under the size specifications because I was running out of filament on my 3D printer, and I just wanted to see if I could make one of the lightest motors. And you can see all the parts here. Next slide. So these are the electromagnetic diagrams. The lines are representing the coils of wire, and you can see that the current goes in through the brushes and then goes across the coil, and that produces a force. And you can see it at the different angles here. So you can see at 45 degrees, there's actually no force produced. It's just a dead zone, which was actually one of the big challenges in making the video, because it has to start at a certain point. It can't start in that dead zone. So I had to get a little tricky to figure that out. Next slide. This is just a picture of my 3D printer and some of the prototypes I made. So that was actually when I was thinking of going full size, the maximum, specifications that we could do, but I ended up shrinking everything down to this size. So it's quite a bit smaller than most people's. And then this is the video of it running.
Rob, you're in that video. Did? Rob, you're in that video.
And if you might not be able to see from the video, but I actually put a little shoe, a little wedge on the end of the bat, sort of like a golf club, to help kick it up more and try to get some more distance on there. It did all right. And I just want to thank Dr. Chang-Siu and Professor Clyde for helping us with this. And of course, Aaron Cole and Chris Muehlhauser with the Makerspace and ordering everything. And I didn't put it on there, but I really do want to thank the ET department for letting us do this. I was really disappointed at the beginning of the semester when I found out we weren't going to do a project, and then we made it work. And I think it was definitely worth it.
Yay. All right. Thank you, Aidan. Awesome. Okay. Close this out. Okay. The next one up is Rob DeMello Souza. Okay. Let's go PowerPoint. Ooh, that was quick. Nice. PowerPoint's learning.
All right. Hello, everybody. My name is Robert DeMello Souza. Thank you all for coming. We really appreciate it. And so here you can see my motor design. On the left is the final product, what it looked like at the very end. And on the right, you can see the exploded diagram of all the different components that made up my motor. Next slide, please. And here are the electromagnetic diagrams. So as you can see on the left, this is like the normal operation state. This is when the brushes are touching the commutator sections perfectly and there is current going through the red coil. So as you can see, the red coil has current going in and at the top near the north magnet, and this makes the Lorentz force and creates a counterclockwise rotation or a clockwise rotation. And on the right, after 30 degrees of rotation, you can see that the brushes have shorted out the two commutator sections, but this is all right because the force is still in the same direction, the clockwise direction, and everything is still working as it should. Here are some pictures of the development process. So a challenge that I had was getting all the wires to fit in between the commutator section in the left image, getting all the wires to fit in between the commutator section and the rotor. And so I actually had to do less wraps on my rotor because there wasn't enough room to fit all the wires. But in the end, I got it to work. As you can see in the middle image and the right image, those are the two final products kind of the wrapped rotor. Next slide. And here's my video. All right, here we go, 24 volts.
I know, we're worried about this stuff, yeah. Woo! Oh, I missed how far away.
All right, here we go, 24 volts motor test.
Nice.
I think it's
3, 2, 1, now.
Ooh, slow-mo. Oh, nice little foot, just like Aidan's. I like that. Very cool.
all right. Here. And the results were that my motor weighed 1.08 kilograms, which is about 2.2 pounds, I believe. And it went a distance of 8 feet 5 inches. And of course, I'd like to thank Dr. Chang-Siu, Professor Clyett for all the help throughout the semester, all the support. You know, I'd never done something like this, so designing it was really challenging, and they were always there for me. And of course, Aaron Cole and everybody in the makerspace for facilitating getting our parts and making this project so easy. And of course, my peers for always being there for support and letting me borrow their tools and such. So,
Awesome. Yay, Robert. Great job. Okay, let's go to the next. All right. The next is Moises Rias. Okay. Let's go PowerPoint.
I'll just introduce myself in the meantime. So I'm Moises Rias. My motor's coming up.
Ooh, ooh. There we go.
Okay, so here's my design of my motor. And even though we've all kind of have like the same concept on the motor, it was kind of challenging just coming up with designs to actually make it work. So here we can see an exploded view of my motor, the CAD designs. And if we look at it from a top view, you'd see the end cap on the left, and then inside is the rotor inside of the stator, and then the magnets on each end. And then, yeah, we can see the commutator and the two brushes, and then the other end cap, which is the one that we see in the exploded view in the back, where the brushes would go. So yeah, we can move on to the next one. So these are my diagrams. So the magnetic field is shown as the B, so it's going from right to left, from north to south, and then as current is coming out of the basically out of the image on the right side and then going into the board basically on the left side, that creates a force up and then a force down counteracting on the other side to keep it moving. And then the 30 degrees shows a dead zone, so there's really no force being created, but the magnetic field is still there. There is current coming out, but because it's not directly just because the wires are not directly in front of the magnets, it's not creating any force. So the momentum just keeps the thing moving. So some pictures. After I put my motor together and did the first test run, my coils came loose and I had to undo about 100 feet there, or I should say about 70 feet, because there's 100 feet on each coil here. So there's a total of 300 feet that I had to wind by hand. So that was a little tough. So yeah, after putting it all together, we can see after soldering it to the commutator, and then here I put a picture when it was all put together. And then the top is just spacers, just so we can see. And I wanted to leave room so we can see the inside of what's happening. So hopefully, so yeah, I had a whole bunch of fails because my commutator came loose.
Nice slow-mo. Nice. Beautiful.
So I kind of went, yeah, like 5 feet, 8 inches or so. The best try I got was 7 feet, but I can get that video.
Yes, very good.
So yeah, distance, so 8 feet, or 5 feet, 8 inches or so. It was about 30 inches off the ground. And some acknowledgements to Dr. Chang-Siu for always having time to answer my questions, even though he has a super busy schedule.
All right, Moises, thank you so much. Great job. Yes, very good. Okay, let's move on to the next one. And we have Tyler Gard.
Hi, everyone. I'm Tyler. So here is my motor design. I got the main components, the stator, rotor, and then the 2 end caps. And then I chose a 6-magnet 3-coil design. And so you can see my design, I connected all 3 coils together. So if one coil is being energized, they were all being energized. And then in the upper left-hand corner, you have the second right-hand rule. And so this is how we're going to determine our Lorentz force. So we have our current orientation is represented by the circles with the X's, and that is current going into the board. And then circles within circles are current coming out of the board. And then your magnetic field is represented by the B arrows, and those are determined by the magnet orientation. And then if you use that right-hand rule, you'll find that the motor rotates in a clockwise fashion. And then if we move to the second diagram, this is just showing a orientation of the rotor where there are no magnets and then also no current. So this is going to be a no force area. The biggest challenge to this project was the 3D printing and design aspect. It was, you may have your dimensions and everything perfectly, but your 3D printer wouldn't want to cooperate. I had to reprint the stator probably like 10 times because right when it started, it wanted to warp a little bit, and yeah, it was causing a lot of issues. So I'm happy to get it all sorted out though. And this is my test.
Nice. Ooh, good, very good.
Yeah, so this resulted in about 8 feet, and my motor was 3 pounds, and that was the finished design of everything put together. And then I want to thank Professor Chang-Siu, Professor Clyett for all their help in this, Mr. Muehlhauser for the logistics, and then Ms. Cole for all her help in the Acura and 3D printing tips. Those were super helpful. And then ultimately the ET department for allowing us to do this. It was a lot of fun, and I feel like I learned a ton. And then lastly, I want to thank my mom and dad for their willingness to put up with listening to a 3D printer run for a month straight. Not very quiet.
Very good, very good. Great job, Tyler. Great job. Yay.
Thank you.
Okay, so what do we got next? We have Daniel Isaacson.
Good morning, everybody. My name is Daniel Isaacson, and this is my motor. Like everybody else's, I have the exploded view in the front. As you can see, it's made out of 4 main parts. I have an end cap, 4 spacers, my rotor, and my stator. We can go ahead and the next slide. My electromagnetic diagram was a little tricky to understand at first. I have 6 alternating magnets and also have 3 coils that are running in parallel with one another. In the first diagram, you can see that each section is being connected to the positive and the negative brushes. They're all energized at the same time. In the second diagram, we can see that when the brushes are actually touching our insulated section of our commutator, there is no force being created. So 6 of my points, I have current going to every single one of my coils, and then at 6 locations, no force being created. Next slide.
Oh, really?
Okay. Sorry, went one too fast. There we go.
So my largest challenge when creating my motor was wrapping my rotor. It took me about 9 times to get the successful first wrap. I had to construct my rotor so I had limited space on the sides of the motor. So it took me about 8 hours to make sure that each coil of wire was perfectly wrapped right next to one another, as you can see in like the mirror finish in the second photo. Thanks to Jake Paxton, I learned a technique of using a wooden dowel and the wire in the fourth photo, and that substantially helped wrap my wires nicely packed.
Oh, really? Okay, here we go. A little bit less.
Nice. Play one more.
Oh, really? Okay, here we go. A little bit less. Oh, really?
So special thanks, first and foremost, to Professor Chang-Siu and Professor Clyett for those late night Zoom sessions going over all the electromagnetic diagrams, and the engineering technology department for allowing each student to get a 3D printer. This was crucial to my senior year, this project, and I was very upset if it wasn't going to happen, and we made it work. Everybody in their unique location. Miss Cole and Mr. Muehlhauser for acquiring all the parts for them, for us, and distributing them, and my friends here at Cal Maritime that we've stuck together through this pandemic, and we've worked hard, and through Zoom we've made it work. My final weight for my motor was 3.08 pounds, and I traveled 14 3/4 of a foot.
Wow, pretty good. All right, great job, Daniel. Nice. Okay, Mr. Jacob Paxton, you are up.
Are we still going in alphabetical order?
Oh, what is this? Enable external content? Yes, we'll enable. Yep.
All right. Hi, everyone. I'm Jacob Paxton. Here's my design. I made it into only 3 pieces where I have basically everything built into my end cap and stator. End cap and stator, yeah. And so the rotor went through several iterations of design, but eventually that was the final product. Next slide. So here are my diagrams. We've got current flowing around here, comes out through here to the negative side. And I did a 2-pole, 2-coil, so it's really simple, but I was able to get all the tolerances pretty tight. I used a whole lot of wire, and it ends up rotating in a counterclockwise manner. Next slide. So here are some of the designs that I started with. I ended up practicing by wrapping one of my rotors once just to see how it worked, and that ended up making me completely redesign it to make it easier to wrap, so I could wrap kind of in a way that was more efficient. And so here's the final product. I was really excited of how it turned out. I thought it looked really nice. And doing some of these small tweaks to my design ended up making it a lot easier, and I was able to get a lot more coil wrapped in there than when I first did it. Next slide. So here's the video.
Please YouTube play. Yes.
Very good.
All right. One more time.
Huh? Very good.
Very good.
So my final distance was just under 10 feet, and I definitely had a heavier motor. It was almost 3.5 pounds, so it was really heavy. But I really wanted to thank Chang-Siu, Professor Clyde, and Aaron Cole for helping with everything. So that's my project.
Yay! Great job. Thank you. Sorry for going a little out of order, gentlemen, ladies and gentlemen. I accidentally had your slide as Jacob Pax instead of Paxton Jacob. So sorry for the little bit of confusion. My bad. Jacob's like, why am I going now?
Totally threw me off.
Sorry about that. All right. Blake, you are next.
All right. Good morning, everyone. My name is Blake Johnson. So I chose to pursue a classic cylindrical design with an emphasis on compactness and low rotating friction. The heart of my design is in the axially locating spacers, which are sized to ride on the inner bearing races and provide just 20,000ths of an inch of axial play within the stator and end caps. Further, there is a 30,000ths of an inch clearance between the rotor coils and the magnets to capture the maximum magnetic flux and thus the Lorentz force, which we can see in the next slide. So this design features 0 dead zones with a maximum force scenario on the left and the minimum force on the right. With the given orientation of the brushes, magnets, and rotor coil design, the direction of rotation can be either clockwise or counterclockwise, depending on the positive and negative connections, and thus flow of positive current. So on the next video, we see using the provided power supply of 24 volts and 15 amps. And that gave a very consistent, I think we got our results 5 times of about 0 inches. And then the next video shows a car battery as a power source.
We are more than 2 feet away. Safety glasses.
Ready?
Yep.
As you can see, it's about faster than the blink of an eye. And had we properly set up the T, it would have gone much further than that previously given 3 feet. So final weight we had was 1.437 pounds, which includes the bat. And then I want to give a huge shout out to cadets Andrew Luft and Colin Whalen and Professor Chang-Siu for helping this project become a success, even through some of the trials and tribulations we faced. The ET department for bringing this together, and my cat for motivational support and helping me on my project, as you can see there. Thank you.
Yay, Blake. Very good. Todd the cat. Okay, next we have is Michael Kostrikov all the way from Russia. Is that correct, Michael?
That is correct.
Okay. Take it away.
So my design was pretty simple. 3 coils, and on each side you have 3 magnet slots for a total of 6. You can see the stator, the rotor, and the 2 end caps. Next slide, please. Here are my 2 electromagnetic diagrams. The purple wires are hot, while the black wires are, there's no current passing through. So you can see the wires as the commutator section touches either the positive terminal or the negative terminal, current flows through to the other side, which helps us to create our force, as you can see on the left and the right, BIF, Lorentz force. Now, since I'm living in the middle of Siberia, I wasn't able to receive the parts that were mailed out, so I had to buy everything myself. I had to fly to Moscow to get some parts. I also had to fly to St. Petersburg. You can see where I got all my parts. Next slide.
Nice, nice. All the way from Siberia.
You can see my distance, my weight. I want to thank Professor Chang-Siu for providing excellent support. He was just always available to help. And thank you to Cal Maritime for providing support to purchase the parts. Even though I had to buy my parts, I was still able to get reimbursed. So thank you.
Awesome. Very good, very good. Thank you, Mike. Okay, so the next we have is Mr. Edward Lee.
Okay, hi everyone. My name is Edward Lee. Here's the overall design of my motor. As you can see, it's pretty standard, 2 end caps, 1 stator, 1 rotor. Next slide. Here's the electromagnetic diagram of my motor. As you can see, at theta equals 0, there are 2 dead zones where the net force is 0. This is because the current going into the page creates a force going down, and the current going out of the page creates a force going up. So those cancels out. But for these regions here and here, because the current only goes in one direction, it creates a force that ends up creating a counterclockwise torque. At theta equals 45, you have a bit of the same, except now you have a commutator shorting issue. But that's okay, because it just means that these 2 coils on the left and right just won't have any current flowing through them. The coils on the top and bottom do all the work, and through the same process explained in the last one, a counterclockwise torque is created. Next slide. So the biggest challenge I had was the fact that too many of my prints ended up being unusable just because they were warped or slanted or caved in, or the holes were just not the right size. My solution was 1, tighten the belt on the motor, 2, level the bed after every print, and 3, I loosened the wheel on the x-axis gantry, because I noticed when I moved my nozzle left and right that I would feel this bumping. And as you can see, there are a lot of rejects. I think I had 9 rejected end caps. So that's quite a bit. Next one. All right, here's my video.
Nice, solid hit. Oh, very good, very good.
Okay. And here are the results. My motor was 1.5 pounds, and the ball went a total distance of 64 inches, and that's measured from the bottom of the nightstand, not the top. And I want to thank Chang-Siu for making us do this project. I know he wanted me to say this, but it is true though. I was kind of angry when he first made us do this, but then as everything kind of came together, I was like, oh yeah, this is actually pretty cool. I should be thankful for Chang-Siu for making us do this. And I also want to thank my mom for recording my video for me.
Yay! Hey, just to remind you, Edward, you're the one that said it first. I was just like, hey, can you?
But it's true. It's true though.
Can you say that again? Tears. Okay, tears of joy. All right, Mr. AJ Luft in the hot pink here. Is that right?
Hello.
Yep.
Hello, I'm Andrew Luft. This is my motor. This is an exploded view, pretty classic. End caps, rotor, stator, commutator, brush holder, and magnet slots. These are the electromagnet diagrams. There's quite a bit going on because I decided to do a 4-pole with 12 coils. The commutator was a bit small for the brushes, so there was no instance where a single commutator segment on each side would be energized. So it's either splitting 2 or 3. The diagram on the left shows when 3 commutator sections are being touched by a brush. And in such a scenario, it's just a matter of quite a current split, which led to load issues. But essentially, there was a pretty consistent rotational force. And the diagram on the right shows when the commutator is split in 2 segments. And it's a little bit better force that way and higher current. Go to the next one. Here's the launch.
Safety glasses, 42 inches, button. Motor test, take 1.
Nice.
Not take 1. Definitely not take 1. I'm going about 12 feet. And this is the real distance launch.
And what were you using to power it for this one?
This would be Cullen Welland's Toyota Tacoma battery.
All right.
We're ready. Hello.
You got to do it again. I wasn't ready.
One more time. I think we got to play that one more time.
A little bit further that time.
We're ready. Hello.
You got to do it again. I wasn't
One broken bat later. So the distance result of using the power supply is about 12 feet. The weight comes out to, with the bat, roughly 3 pounds. The real distance with the car battery was more like 40 feet and about 25 feet of height. I'd like to thank Dr. Evan Chang-Siu for the assistance the night before with some load issues, helping us troubleshoot. Professor Thomas Clyott for all the support. And of course, Cadets Cullen Welland and Blake Johnson for really just bearing down. The ET department for making this all possible. And Cullen's car battery and Blake's cat, Todd. So.
All right, awesome. Very good, AJ, very good. Go Tacoma. All right, next we have up is Mr. Reese Makarowski.
Morning, everybody.
Give it 1 second. Sorry, Reese. There we go. Okay.
All right, so here we go. This is my motor design. I went with the 2 poles, so magnets on each side, and then 3 coils and 3 commutator sections. And then here's the electromagnetic diagram. So there's only 2 positions it can really be in. On the left here, we have power through all of the coils. And that's because the commutator in the middle is touching the brushes, and that bottom one that isn't touching the brush is actually putting those bottom 2 coils in series with each other. On the left and right upper parts, you can see that there's a current creating a force that causes a counterclockwise rotation. And on the bottom, there's 2 counteracting forces that actually just cancel each other out, which allows the motor to still spin correctly. And on the right side, we have one of the coils completely unpowered because it's touching 2 positive leads on the commutator. And on the right side, we have current. This is the largest force that the motor will get, is when current's coming out of the page right there, right next to the magnet on the right. And the force is counterclockwise. And there's 2 smaller forces from the north magnet on the left side. And so this is my rotor design, V1 and 2. So in the first one, I wanted to get as much room for wire wraps as I could. So I put these giant circles in it. But because the magnetic field from the magnets drops off so quickly from distance, it was actually better to have those flats in the V2 version to get all the wires up at the top right next to the magnet. And I still fit 200 wraps per coil, which was 400 wraps interacting with a magnet at once. So it worked out pretty well. And then here it is.
Nice.
All right. And I want to give a big thanks to these 5 cadets here. They helped me physically and mentally get through this project. We all worked in collaboration quite a bit there. And of course to Mr. Chang-Siu for getting us to do this project. I was in the same boat as Edward. I wasn't super excited about it at the start, but as we got into it, it was definitely worth doing. It was very satisfying. And of course, Aaron Cole for getting the makerspace together and getting our parts together for us. Mine went about 9 feet, and the weight was 1.42 kilograms, which I think is about 3 pounds.
Very good. Very good.
That's
All
it for my
right.
motor.
Great job, Reese. Nice. Okay, so let's go this. And the next we have is Mr. Chase Melhop.
Hi, everyone. So I decided to go with a 3-coil 6-magnet motor. So I have my magnets spaced out on the left and right of my stator. And I actually printed a separate brush plate because I thought that I would have to print a lot of extra plates, which I did have to do to get those brushes to fit correctly, but it did work well in the end. These are my electromagnetic diagrams. On the left, you can see there are 2 coils energized because the green and blue bars, those represent my commutator sections. even when there are 2 coils energized, there still is a counterclockwise force that when getting the motor to work correctly. And then ideally there will only be 1 coil working at a time, as you can see on the right. And that gives me the most amount of force because that's when the most amount of coils are closest to my magnets. These are some pictures of my motor in the building and after I built it. The top left is my rotor with my wraps. I got about 90 wraps of 20 gauge wire around each coil. And in the middle and the top, you can see my magnet locations in my stator. And on the top right, you can see my rotor inside of my stator. And the other pictures are, the middle bottom is a picture of my brushes, and the other pictures are just pictures of my motor together and disassembled.
Nice. I'll play that again. Very good.
And the distance was about 14.5 feet. It weighed a lot because I did create this giant base plate to mount it, which I didn't actually really use as much as I hoped I would. So that kind of messed up my weight, but I did hit it 14.5 feet, which is great. And I would like to thank Professor Chang-Siu, Professor Clyett, all the boys, Aidan, Daniel, Reese, Rob, and Jake, Aaron Cole, and Chris Muehlhauser for getting all of our parts out to us in a timely manner and keeping it all organized and helping us when we had issues. And I'd also like to thank the ET department for making it possible for us to even do this project, and Hendrik Lorenz for making the Lorenz force so simple so that we could actually, all of us 26 students can figure it out and properly get it to work on our motors.
Yay! I love the picture. I actually did not know that Dr. Lorenz looked like that. That's awesome. Thank you. All right. Who do we have next? Mr. Pat Mullen. All right, take it away, Pat.
Hey everyone, my name is Patrick. Here's my project. Next slide. All right, so my design was 2 poles with 3 magnets per pole. And I use all 12 commutator slots with 6 coils. So I thought that with more coils firing and I only have 1 revolution, that I might as well have the most continuous torque and least deceleration of the rotor possible. And I cross B due to the Lorentz force shows that the force is going to be in a counterclockwise direction. So I did a little extra and I made a little jig for a reflective IR tachometer just to see how much I can get the motor up to speed at max speed. You know, we're looking at almost 5,000 RPM. I even got I had tape holding my stator coils or the rotors together, and they bowed out and caused some friction on the tape and sort of melted and gummed up the whole thing after I'd already tested it. But a couple extra pictures of the soldering manufacturing process. Some of my printed parts had the hole shrink down, so I had to, you know, drill it out a bit. Let's watch the video.
Nice. Solid.
So the results got about an average of 11, 11.1, 11.2. So, and my weight 2.25 pounds. Special thanks to Aaron Cole. The logistics is usually half the battle. So thanks for getting us all the parts. Same with Chris. Goes without saying, Chang-Siu. I mean, all the knowledge you bestowed upon us, and my own dad, Ed Mullen, for, you know, wisdom in manufacturing and for extra hardware. Thanks, everyone.
Yay, Pat. Great job. All right. Next, we have Well, Jacob Paxton was supposed to go at this time, but we have, let's see, Skylar Sam.
Good morning, everybody. So here's my overall design. On the left is a bird's eye view, and on the right is my 3D CAD exploded view. So for my motor, I chose 4 magnets, 3 armature coils, 6 commutator section, and then 2 brushes. All right, so my electromagnetic diagram, you can see the black wires are the wires that are going to be energized, and the current will enter into the page on the right side of the rotor and comes out of the left side, which creates a counterclockwise force on the rotor. And at 30 degrees, there's 2 coils that will be energized at the same time. And again, a counterclockwise force is created. So the top has some pictures of a timeline. Similar to Dan, I had to redesign and rewrap my rotor. I realized that I wouldn't have enough space between my end caps and my rotor. And the second time around, I was able to wrap them a lot neater and fit more coils in there. And also without flux, one more challenge was without flux, it made the soldering process a lot harder. And so if I were to repeat it, I would definitely purchase flux to help with the adhesion. And then I'll show my video really quick.
Boom, nice. Very good.
And a quick thank you. Results, it went 6 feet 3 inches, and it's about 1.2 kilograms. Thank you to Professor Chang-Siu and Professor Clyett for all the outside help outside of class. A quick shout out to Moises for additional help, and my roommates for letting me use up all the tables in the apartment.
Yay, great job, Skylar. Great job. Okay, we have, the next one is Mr. Gage Sturgeon.
Okay.
Gage, please take it away.
One sec. Mic's not working.
We can hear you.
Can you hear me now? Yep. This is my webcam mic, so it might not sound as good. So here is a picture of my motor in an exploded view. So you can see my stator in the center, and I have a brushed end cap at the end with an insert to allow the brushes to be epoxied in easier. And the distance where the magnets are supposed to go into the stator is a little long, so I added magnet spacers so I didn't have to epoxy the magnets in, and they would just get clamped in by the awl thread around the outside of the brush end caps and rotor. And then you can see, I accidentally put the arrow for the rotor pointing to the stator when it's supposed to be pointing to the orange part in the center. That's what goes and spins in the center. We'll see in this minute. Next slide. So here is a picture of my electromagnetic diagrams. On the left-hand side, you see it in a non-shorted position. It allows current to flow through all 4 of my windings. So I have a 2-pole design, except the poles form around the whole outside of the stator. And so as it flows through in the non-shorted position, it flows through one coil, it goes through the unused commutator bar, and goes out through another coil and goes back into the negative side. And that causes a counterclockwise rotation. And on the right side, you see a shorted position. And that only allows 2 coils to have current flow through, but it still produces the same counterclockwise rotation due to the Lorentz force in the top right corner. You can go to the next slide. And so here's an assortment of images from my design process. On the left-hand side, you can see what the wrap looked like when I was completed. And on the next photo, we see my switch and mains routed into the power supply. And in the next photo, we can see after I epoxied my commutator and rotor to the shaft. And then next photo, I'm testing to make sure I didn't accidentally short between the commutator sections. And you can see in the back that there's infinite resistance. And then I'm soldering the connections. And in the end is where I epoxied the brushes. And then that's the final construction and T where I hit the ball. We can go to the next one and we can start the video.
Nice.
It hits right before that line. And the next one. And so the results was my distance was 9.33 feet and the weight was 2.375 pounds. And thank you to Dr. Chang-Siu for assisting with the project, and anybody who helped, like Aaron Cole and Professor Clyde, who assembled all the kits. And additional thanks to the ET department for allowing the funds to go towards us to be able to complete this project.
Yay! Great job, Gage. Great job. Okay. And next we have Mr. Skylar Ulrich.
Hello, everyone. My name is Skylar Ulrich. So here's my overall design. 4 magnets, 4 coils, and 4 brushes. So you can see here 3D design in SolidWorks, the end cap, the rotor, the stator, and the other end cap. I decided to put windows in the end caps so I'm able to see the motor function. Yeah, next slide, please. Here are my electromagnetic diagrams. So the first diagram is the idle state, which is the dead zone. You can see the brushes are labeled and the magnets as well. So I had 2 different north magnets and 2 different south magnets, and 2 positive brushes and 2 negative brushes and a 4-sided commutator. So looking at the operating state, you can see the current direction, and Lorentz force is also labeled. B represents the flux from the magnets, and then the F represents the force. So basically pointing in the direction the motor will spin, which is clockwise. You can see with the circles and the X's represent the currents going into the page, so flowing in that way into the wire. And then the circles represent the current coming out of the page. So the current would be coming out into the commutator on the negative end. And I also decided to do a shorted section commutator, which you can see in one of those photos there. So the first 2 photos are the full build assembly. The third one is the brush assembly along with the rotor wrapped. And the last photo is a stator with the magnets in it. And here's my video. Alrighty, so unfortunately I had to use a different power supply, so my results weren't that great. But my ball traveled distance 2 feet, my motor weighed in at 2.4 pounds. So I'd like to thank the Makerspace staff for being flexible in their schedule, and Professor Clyde for helping me out during the labs, and most especially Professor Chang-Siu for meeting with me 200 times to figure out what was wrong all the time. So thank you.
Yay. Thank you, Skylar. Good perseverance. All right. We have 4 more, ladies and gentlemen, 4 more. All right. Up next is Anthony Voto Bernales.
Yeah, hello. I'm Anthony. And so as you can see here, we have my overall design, and you can see I have exploded views and then what it actually looked like when it was all put together. And then that arrow, I thought that I had put one there that was also going to the other end cap. And then you can see I have my stator and my rotor too. And so these are my electromagnetic diagrams, and you can see that in the one on the left that we have our dead zones, where basically the motor won't spin. And then as you can see on the right, we have that we were rotating in the counterclockwise position, and that we have the 2 coils energized. And these were just some pictures that I had taken along the way. And just like other people, I definitely had a lot of printing issues. And then when I did get prints, sometimes they weren't to the right tolerances. And then it was honestly pretty hard actually getting the magnets into the slots. Like they really like clamping or like trying to cling on to each other, turn around. And so here was my video of it.
Nice slow-mo. Ooh, good hit. Very good hit.
And then yeah, that was just another try that I had gotten.
Very good.
And yeah, so my final weight was 2 pounds. And the max distance I was able to get was 93 inches. And then I wanted to give a shout out to Professor Chang-Siu in the ET department for making the project possible, and definitely to everyone in the makerspace for printing parts for me at the last minute. And then also to my friends who were there helping me and answering my questions.
All right, great job, Anthony. Okay, we have 3 more. Okay, James Wang.
Hi.
There we go.
Hi everyone, my name is James. This is my motor design. On the left side is my expanded view. As you can see, there is 4 parts: the front end cap, the stator, rotor, and the back end cap. On the right side, there's the dissected views of the overall design. Each part is labeled. The magnets are ×3, 3 by each size, 3 coils, and 6 commutators. Next slide. Here's my electrical magnetic diagram with the magnets on the left on the north side, and then another 3 on the south side. And it rotates counterclockwise. Yeah. Here's some pictures of the 3D printer with my dog staring at it all night while it's printing. Some difficulties where I have to pull the commutators inside the brushes, and shorting low wires on the commutator. There's an optical
students.
Very good.
Next slide. Here's the video demonstration.
Boom. Nice.
Yep. The results are 8 feet 9 inches. The height was 30 inches, and it weighed about 2.4 pounds. Special thanks to the engineering department for making it all happen, and Cole for the logistics and making it convenient for the pickups. My fellow ET members, and Chang-Siu professor, and my dog Hero.
Oh, great job. Okay, we got 2 more, and we are doing well on time. We're at 10:43. Okay, Mr. Colin Whelan.
Good morning, everyone. My name is Cullen Whalen. This is my project pulling up right here. So on the left, you have a isometric view of my motor. And then both pictures on the right-hand side of the screen are exploded views. I use 6 magnets located in 2 poles. I had 3 coils, each with 130 wraps of 24 gauge magnet wire. Yeah, we can go to the next slide. Right here, you can see I was able to use with some of my ME colleagues some magnetic flux simulation softwares that allowed me to actually simulate it. So you can see right here when the coils are energized, the current's going in at the top, which, you know, as you can see, the magnetic flux is going up, which causes the anti-clockwise rotation of the motor. So we can go to the next screen. Right here, you can see that one of the interesting things that we found during the simulation was that the actual shaft and the steel in the bearing definitely interacted with the magnetic flux and caused a lot more fringing than was expected from these magnets, even with the relatively large distances in between them. And then you can see I made a metered power supply in one of the small photos right there, just to help troubleshoot while working with it. And yeah, so we can go to the video on the next slide.
The music.
Yep, so after that, the results were I got 12 foot 4 inches as my distance with a weight of 1,295 grams, which is 2.7 pounds. My acknowledgements are Daniel Isaacson, Robert, Andrew, and Blake, all cadets here at Cal Maritime, Professor Chang-Siu, and then everyone else who helped on the back end, Aaron Cole, the makerspace, and the ET department for making this all happen. And my wife for listening to the 3D printer print for over a month straight continuously in our house, which is awesome.
Yeah, I acknowledge the wife. Very good. Great job, Roland.
Thank you. Thank you.
Okay, and we have our last presenter of the day, and then we'll do the results. It is Jack Whalen. They are not brothers, but
Yeah.
they're both awesome.
Just a coincidence. Okay. So here's my motor. Just a little bit of an exploded view. You can see the rotor, stator, and end caps. This has a 6 armature coil, 2 pole, and 6 magnet design. So here you can see like just 2 situations that only the coils that are actually activated are drawn. So you can see just how the force and magnetic field would be like during the operation of this motor. So I actually created a new bat design just to put the center of mass like in the center. It's kind of a nice thing you can do with Fusion 360. You can see where the center of mass is. Here's a quick video. I was able to get it to go 15 feet and 4 inches. Wow. And the final weight was 1.064 kilograms. And I'd like to give a thanks to Evan Chang-Siu. He really made this possible, and Thomas Clyett for giving me some good pointers.
All right. Yay, Jack. Okay, now the moment you've all been waiting for. All right, let's close this out. It's the results. It's the results. Okay, let me pull up the results. So let's not give this away before it. Oh my God, no, don't give it away. Okay, hold on. Okay, good. That was fast. Okay, so the very first. Well, before we want to show go over the results, I just got to say I'm so proud of you guys. You know, I remember having a conversation with these wonderful seniors, these ladies and gentlemen here, and I personally was like, I don't know if I want to do projects. And there was, you know, there's with natural feelings, some of the students were like, but there were a lot of students that were like, let's do it, let's do it. Tom Clyett, my buddy, my colleague, he was like, Evan, you got to do it. You got to put them through their paces. They want to learn. And even the ones that might go, let's do a final, they're going to appreciate it at the end. Our Dean Neto, she was like, let's do this. We'll figure out a way. And I'm like, okay, all right, let's do it. Fine. And you guys all pulled through. Aaron and Chris, they put everything together behind the scenes when I couldn't be there physically. It was just awesome. And to see everyone build up momentum and get everything going, wow. So yeah, the results here just show the numerical performance, but really, I'm proud of each and every one of you. So I just want to make sure that your feelings on the results are removed from the pride I'm feeling for you guys, okay? And the pride you should feel for yourselves. So I really thank you all. Okay, let's do the results. So created a little MATLAB script just for funsies yesterday. So all the students told me their weight and their distance. And so the first thing here is the weight. So we're going from heaviest here to lightest, which means the lightest gets the most points and the heaviest gets the least points, unfortunately. But this is the breakdown. You can see everyone's names here. So you got Blake here, the lightest. So mission accomplished, right? And then unfortunately, Chase was heavy, but I think you knew that. And everyone's in between. Okay, so that's the normalized weight score here. And then the next one is the distance. So here we go from least to greatest distance. Ooh, we were close up here. All right, so here we go. And this is your normalized score for distance. And then when we factor in the weight, we have everyone's score. So congratulations, third, second, and first place, Pat, Dan, and Jack. These are your relative scores. Very good. But now you can see how you guys place. You see all your scores. You can see how you rate relative to each other. You got your bragging rights, right? Like you got AJ and Colin here, buddies. Oh man, I feel like AJ is never going to hear the end of it from Colin, right? It's going to be fantastic. All the trash talk that's going to happen now. And
look how close AJ was.
Right? Oh my goodness. So yeah, Chase and AJ, look at this. Oh my gosh, 0.1%. Oh yeah, I'm gonna love it. So I will send out this Excel to the students, and the students are going to be making YouTube videos of their motor, so we'll be posting all that stuff out. And lastly, here's the results, right? So all the students will get that Excel file. And I just wanted to end with this. This was as many selfies as I could get at 7 a.m. this morning. And this is just to show you every student having their own 3D printer in their dorm or their house, able to work remotely, safely, and still accomplish these amazing projects, even though we couldn't be physically together. But thank you all my friends and past students and colleagues that came and attended and supported these students. Thank you for all this faculty and staff. This adds a lot of meaning, and so we really appreciate it all. I think that's it. We have concluded. This is your fall 2020 ET350 project experience. Thank you again, and I think we're signing off. If there's anything that anyone would like to say, please say it now.
I'd like to add a few words. This is Lina Neto. I'm really impressed with all your work, like I put in the chat, especially that you had to work under very different circumstances. And thank you to Professor Chang-Siu and Professor Clyett that apparently had extra Zoom meetings with you to help you survive and be successful with this class. It's really wonderful. For those participants in this session that are from industry, we would really appreciate if you could send to Professor Chang-Siu in writing by email your impression. If you have comments for future improvement, please send it, because we use all your input to help the cadets succeed, to improve the course, and to see how it meets your needs to the industry. So thank you all for participating and being here. And above all, the cadets. I know it's hard, but it will pay off. It's your future. Thank you all.
Thank you. Thank you. Yay. All right. And we are done. I'm going to go take a nap. See you. Bye.
Thank you.
Oof. We're done, gentlemen. We're done, ladies. Good job.
Quite so.
Good job.
Peter.